This is April 2nd, 2017, yesterday, April Fool's Day. I gave a short talk on Bucky Fuller's subconscious demon. And what I meant by that was his quest for a volume 5 in Synergetics and his concentric hierarchy of polyhedra, beginning with, say, a Genesis story of, say, the five platonics taking their duals, combining their duals, and even taking the duals of their dual combinations. In the case of the rhombic dodecahedron, its dual is the cuboctahedron. And that pretty much completes the minimal vocabulary of the concentric hierarchy. It's not trying to be all polyhedra or something. It's just picking a certain backbone and sticking with that, keeping it simple, you could say. Anyway, where Fuller ended up was with two rhombic trichondahedra, if you recall, and their difference is almost vanishingly small, but it's significant. It's mathematically very obvious. If you want to shrink wrap a sphere exactly with a rhombic trichondahedron, its tetravolumes relative to the tetrahedron of unit edge 1D or 2R, is going to be a little bit more than 5. And if you want an exactly 5 volume rhombic trichondahedron, you're going to shrink down the radius a little bit. By radius of the rhombic trichondahedron, I mean from a center point of the diamond. We'll call those the C points. So here's another picture. From C to the origin O, that's what we call the radius of the rhombic trichondahedron. There's also lengths OA and OB. And Synergetics usefully gives us this plane net showing how you can create a T or E module, because there's the same shape, from a perfect square, kind of like origami starts from a perfect square. But we break the rules of origami, and we need to use some scissors, because once we have this top lid, this right triangle, we're going to need to flip B and put it over where A is, and vice versa. We're going to have to flip this lid by 180 degrees, which can lead to some confusion. Just remember that OB is clearly a shorter distance than OA. However, that's what we need to remember to flip. Think of this as OB instead after we flip it, because the longer distance is going to be to the sharper point. Now, what do I mean by that? Let's look at a picture of rhombic dodecahedron and rhombic trichondahedron side by side. You'll see what I'm holding up here. It's important to realize that on both of these shapes, made out of rhombuses, the diamonds have two different angles, a shallower or wider angle and a sharper angle. So on the rhombic trichondahedron, they can come together as 5 sort of flower petals at the sharper edge, and we're going to call those the B points. Whereas if they come together as just 3 faces, we're going to call those the A points. And you can see that in the picture as well. The rhombic dodecahedron is similar. I'm going to pull one of those up. You can see, having diamond faces, not square, unlike the cube, there are 2 ways that the vertices show up and still have concavity, convexity. Remember, if you have 360 degrees, you no longer have curvature. So at these vertexes where 4 meet, you've got the sharp points, and where only 3 faces come together, that's where you have the wider angles. Now it's these wider angles and the shallower points where we're going to make anchor points for both the rhombic trichondahedron and the rhombic dodecahedron. We're going to build both off of that same cube, which for us is volume 3. Even though the edges are square root of 2 and the diagonal is 2R or 1D, we say the volume is 3 because of how we multiply. That was something I showed you in another video, how we multiply in Synergetics. So this is the volume 3 cube, and we're going to talk about the radius of the corresponding rhombic trichontahedron when we build around that. We're going to be asking ourselves, is this number 0.9994 ugly, or is it somehow perfect? So this h again, the radius from 0 to c, that depends on what we fill in for h. And to make the rhombic trichontahedron exactly 5, that h can't be 1. That gives us the E modules, and that gives us the rhombic trichontahedron that's a little bit greater than 5. I say 5 plus. So if we want exactly 5, then we need to use this number h. Now, what is that number? Well, let's go ahead and scale it up. Now, remember, when you scale something up by, like we want to go from volume 5 to 7.5, that's going up by 3 halves in volume. But that means we only have to go up as a third root of that in terms of linear distance. So if the radius was h, now it's going to be h times the third root of 3 halves. And we find out if we pull out our Python and do some calculations using extended precision in this case just for fun. You can also use algebra to figure this out. But I'm giving some exercise to what's called the decimal type, which allows 100 digits of accuracy or more if you want, somewhat up to how much memory you have, how much accuracy you really need. What we find out doing our computations is that the value of h in the case of the 7.5 is exactly phi over the square root of 2, or the second root of 2, if we don't want to say square root. We have different ideas about that sometimes. Anyway, phi is the second root of 5 plus 1, all of that divided by 2. So that number over the second root of 2 is our radius of the 7.5. And that is indicated in the Wikipedia article right there. It says phi over the square root of 2. So really this ugly number, the 0.9994, apparently ugly number, is simply phi over the square root of 2 times the third root of 2/3. So that's pretty easy. It's not all that difficult. So this is actually a fairly beautiful outcome. Here's a picture of these two shapes using the same anchor points, the points of this volume 3 cube. Remember, the dodecahedron, the rhombic dodecahedron, has a volume of 6. So the ratio between them is 7.5 to 6, or 5 to 4. And what that means is that even the volume 5 rhombic trichontahedron has within it a dodecahedron of volume 4, and it in turn within it has a cube of volume 2. Now none of this should be too surprising because we know from ancient times how a cube can inscribe into a pentagonal dodecahedron. And the pentagonal dodecahedron, one of the 5 platonics, is a parent of the rhombic trichontahedron. So the fact that a cube will inscribe in a rhombic trichontahedron is a well-known fact. However, you're going to find it rather difficult, I think, to find much mention of this other relationship between these two rhombohedra, the 5 to 4 relationship, as shown here. CSN Esoterica is a little video, music video with the music of famous Jimmy Watt extolling the good fortune we have to now have this ratio under our belts as well. So that gives you some understanding of this chart, and if you're reading about synergetics, at least the polyhedra part is probably going to start to coalesce into a familiar kind of a neighborhood, kind of a Sesame Street. I would call this the Sesame Street of Synergetics. The concentric hierarchy neighborhood is your familiar stomping grounds. After a while, it becomes almost second nature, but it takes a while to build up to that. Thanks for watching, and we'll talk again soon.